Okay, let us now start to solve Newton's second law based on the force that we just acquired, negative kx. F equals ma, that's Newton's second law. This is a one-dimensional motion, so let's choose the positive direction to be along the direction where the spring is getting longer. It is being stretched. So of course the force is negative kx because against the direction of the deformation, so that's why the negative sign comes from. Equals mass times acceleration. The acceleration in one-dimensional motion is the second derivative of x with respect to time t. This is what's called a second-order differential equation because, in an ordinary algebra equation, we're looking for the solution, which is just a number, okay? Say a quadratic equation, x equals 1 or x equal to 0.5, whatever, it's just a number. What we're looking for here is a differential equation. The solution to the differential equation is not a number, rather it's a function. It's an unknown function f. Here the variable is t and the unknown function is x. So we are looking for x as a function of t. What kind of function would it be? Well, let's take a look at some common functions, shall we? We have, for example, a power function, t to the power n, exponential function, e to the power t, and so on. Does the power function work? Well, obviously it doesn't, because if we take a look at this equation here, let's say it's t to the power 5, for example. When you take a derivative, what do you get? That's t to the power 4, right? You take another derivative, that becomes t to the power 3. But that the other side still is t to the power 5. The powers do not match, of course, power functions do not work. So, if you take a good look at it, you'll find that this side is x, that's a function. The other side is a derivative, actually, second derivative of the same function. And yet the two sides are always equal to each other. What that tells us is that we're looking for this special function, f of t, such that when you take a second derivative, it goes back to itself, except for a negative sign. Okay, what kind of function behaves in such a way that when you take derivative to go back to itself? Well, obviously, the exponential function comes to mind, e to the power t. Now, does the exponential function work? Well, unfortunately, it doesn't, because when you take an exponential function, you take two derivatives, you don't get this negative sign, do you? Okay, so mathematically, can you think of a function such that when you take two derivatives, it does not only go back to itself, but it gets an actual negative sign? Well, the answer, of course, yes, it's sine or cosine function. For example, if x is a sine function of time, you take one derivative that's a cosine function, another derivative is negative sign. Or if it's a cosine function of t, you take one derivative that's negative sign, another one it's negative cosine. Indeed, it goes back to itself with an actual negative sign. So mathematically, we know that x is very likely a sine or cosine function of time. Now, does that mathematical reasoning have any physical support, physical background? But of course, because don't forget, after all, this is not just a math equation. It is a physical equation of motion describing the oscillation of a block that is attached to a mass, a spring. Now, when you let go of it, the block is going to oscillate back and forth, back and forth, back and forth. So x will alternate between positive and negative values. It has to be an oscillation. Power function is not an oscillation. Exponential function is not an oscillation. But sine, cosine, these are indeed oscillatory functions. So you see, it makes sense, both physically and mathematically, that we should be looking for a sine or cosine function. Okay, so what kind of sine or cosine function? Well, first of all, it makes no difference whether we use sine or cosine, because the only thing about sine or cosine, let me draw something for you. This is t. If it's a sine t, if a sine function is like this, it passes through the origin, right? Now, what about a cosine function? A cosine function starts from here, from the maximum. So basically, I can change the sine function to a cosine function. All I have to do is move the origin of the t-axis from here to there. What is the meaning of moving the t-axis? Well, it is basically saying instead of starting from my stopwatch from here, I'm going to start my stopwatch from there. Now, when you look at an oscillation of a block attached to a spring, you can start counting its motion from whatever position, right? Does it matter when you start your timer? Does the fact that you start your timer here or there affect the motion of the thing itself? Of course not. So therefore, sine and cosine doesn't quite matter to us. So therefore, we're just going to follow the textbook. The textbook chooses the cosine function, so we're going to choose a cosine function too. All right, so let's say x is now a cosine function of time. All right, can we simply write cosine t? What would be wrong with it if I simply write cosine t? Well, that is not right, because after all, the argument of a cosine function is an angle. An angle is dimensionless. It has no unit. And t has, of course, unit. It's time. So therefore, that doesn't work. I must put a constant in front of t so that I can get rid of its unit. And that constant, we call it omega. It has its own physical meaning, which we'll get to later. All right, so cosine omega t, like this. But wait a minute. This whole thing, cosine omega t, is just a number, because cosine function, you know, is just a number. It has no unit. And yet that side is a displacement. It has, of course, the dimension of length. And therefore, they don't match, do they? And I must therefore add yet another constant overall in front of it, call it a. That a has a unit of length. And what is the meaning of a? Well, it's clear. Because the cosine function is never going to be greater than 1. It's never going to be less than negative 1. So basically, this thing varies between negative 1 and positive 1. And when it reaches a maximum or minimum value, positive or negative 1, that is when x equals either positive a or negative a. That is the greatest value of x away from 0. So a really is the maximum distance the oscillation can move away from x equal to 0. And we give it name. We call it amplitude. All right. There's one more thing that we have to keep in mind. If you write x equals a cosine omega t, let's look at what happens t equals 0. When t is equal to 0, the cosine function must go to 1, right? Which means you are definitely sure that the motion was that the moment you start your stopwatch, this thing is right here at the maximum position. But does that have to be the case though? I mean, is it possible that I can start my stopwatch here, or even here, when the thing is not quite at maximum position? Of course I can. So to reflect that flexibility, I can start my stopwatch anytime and start measuring the motion of the object, and therefore I don't want just a pure cosine function. Rather, I'm going to add a little constant in front of it, plus delta. That delta, of course, is an angle. That angle is equal to the whole thing of omega t plus phi, omega t plus delta when t equals 0. Now, this whole angle after the cosine function, as this angle varies, so does x. Okay, so for this reason, we say this angle is called a phase angle. Phase angle. At different phases, you're going to have different values of x. And delta, therefore, is the value of the phase angle when t is equal to 0. So therefore, delta, we call it initial phase, or initial phase angle. So now we have a reasonable or educated guess as to what x as a function of t might be. It is equal to a cosine omega t plus delta. There are 3 parameters here, a, omega, and delta. I used a red color for omega, and you'll see why, because it turns out omega is different from the other 2 parameters, a and delta. Now, this is just a clever guess. It makes sense, but is it really right? We don't know. How do we know that for sure? There's only one way to find out. That is, we're going to take this thing and we're going to plug it in to this equation. We are going to take two derivatives of this function, second derivative that is, put it here, and we put x on the left-hand side. See if the two sides give the same value. If they do, that's great. If they don't, that means our function is wrong. We're going to try something else. Okay, let us now plug in the numbers. Actually, plug in the functions. The left-hand side of the function was equal to negative kx. That's the Newton's second law, the left-hand side, the force. X equals a cosine omega t plus delta. So we plug that in. The right-hand side is mass times acceleration, of course. I'm sorry, there's a plus sign here. It is equal to, when you take a second derivative, there's an omega squared coming out, and cosine becomes cosine with a negative sign. So it's equal to negative m omega squared a cosine omega t plus delta. The question is, are these two sides equal? Well, let me equate these two sides. Basically, I'm equating those two functions. And you see, if you do that, you can indeed make them equal. All you have to do is to make sure that Ka equals m omega squared times a. Now you cross out a, you find that K equals m omega squared. In other words, omega equals the square root of K over m. This is the only requirement which will make our solution valid. In other words, we did find the correct solution to the equation, and that is x equals a cosine omega t plus delta, with only one requirement, and that is this omega cannot be just anything else. It must be the square root of K over m. Let's take a good look at what omega really means. As you know, omega, the unit of omega should be 1 over that of time, so that's 1 over second. What is the true meaning of omega? Well, let's see now. As you know, this whole angle is called a phase angle, and as the phase angle changes, so does x. Let's plot x versus t. Here's a couple of cycles of oscillation. Going from here to there, the motion repeats itself, that's 1 period t. Over this 1 period t, how much should this phase angle change? Well, you know, the cosine function is a periodic function with a period of 2 pi. So as you go from here to there, if the cosine function repeats itself, that means the phase angle, omega t plus delta, must change by 2 pi. Okay, here is the change in the phase angle, delta of omega t plus delta. Now, as you go from here to there, the initial phase, that's just a constant, that doesn't change. Omega is a constant, doesn't change. This t, the time, changes by 1 period, right? So this change in the phase angle is omega times t. And as we know, that equals 2 pi because the motion going from here to there repeats itself. We solve for t equals 2 pi over omega, or omega equals 2 pi over t. Does this ring a bell? You learned from physics 1a in rotation. You have something very similar, 2 pi over t, and that we also used omega to describe it. Do you recall what omega was called by then? It was called the angular speed. The time it takes, how fast a rotation covers a certain angle. If it takes this much time to cover a whole angle of 2 pi, then on average, this is the so-called angular speed. Now, what we have here is something very similar. This also has to do with the angle. So this omega tells you how fast the phase angle changes. So we also have a term angular in its definition, except we don't call it angular speed because this is just an angle. It tells you how fast this angle changes, and therefore we call it angular frequency. It is very much related to angular speed. So now we have our solution to this spring and mass system. X equals a cosine omega t plus delta. Now recall I used red color for omega. So why is omega different from a and delta? You recall that in the solution to the equation, a and delta did not really matter. They can be anything I want. Omega, however, cannot be just anything. It must be the square root of k over m for the equation to be valid. we call omega a dynamic variable. It is different from A and delta. What is the meaning of dynamic variable? Well, this is a variable that's determined by the system itself, by the spring and the mass. It has nothing to do with how I influence its motion. For example, when do I start my stopwatch to measure it? That, of course, is going to affect what happens at t equal to 0. At t equal to 0, is this a maximum of the cosine function or minimal or somewhere in between? That entirely depends on when I stop my stopwatch. If I wait for this mass to go all the way to the end at that moment and click my stopwatch and call it t equal to 0, then of course cosine function must be maximum or positive 1 at t equal to 0, which means this delta is now going to be 0. So you see, I can change the value of delta simply by deciding when I should start measuring the motion. And that, of course, has nothing to do with the system itself. It only has to do with how I measure it, actually precisely when I start measuring it. So you see, delta is not determined by the system, but by myself, the observer. A is the amplitude of oscillation. Now the interesting thing is, if you have a motion with a very large amplitude like this, this is A, and so is this. Then you consider a motion with much smaller amplitude like this. It turns out that the time it takes for the motion to repeat itself, which is the time from here to here, really is the same. It has nothing to do with A, because t has no A in it. Does that make sense? Well, qualitatively actually it does, because what happens is if you pull the spring a lot, and then the spring will have to cover a great distance before it reaches back to equilibrium position, which is x equal to 0. So you might think it takes longer time because it has to cover a greater distance. Now don't forget though that when you pull it a lot, the spring will experience a lot of restoring force. In other words, negative kx will be on average very large. So the acceleration will also be very large. So indeed, it takes longer distance, but also has greater speed. So these two factors cancel out. So eventually, the time it takes for the thing to go back and forth has nothing to do with the amplitude of oscillation. So how is the amplitude of oscillation determined? Who determines A? Well, actually, A is determined by me as well. You see, I have to pull the block away from equilibrium, which is at x equal to 0. I have to pull a certain distance and let go of it, right? Now, how far do I pull? Do I pull by 2 centimeters and let go? Do I pull by 10 centimeters and let go? That is A. If I pull 2 centimeters away from equilibrium and let go, then it's going to go back and forth, back and forth, back and forth. No matter what happens at later, the maximum distance between the block and x equal to 0 is 2 centimeters. And if I pull a lot more to 10 centimeters, then A equals 10 centimeters. So you see, A also is determined by me, the person who initiates the motion, not by the system itself. The system has no choice what A is, what delta is, but it does have a choice about omega. It can determine how fast the oscillation goes. As you know, omega equals square root of k over m, and conversely, the period of oscillation is 2 pi times the square root of m over k. This also makes sense if you think about it. How long does it take the motion to repeat itself? Well, first of all, if you have a very massive block, then of course under the same influence of the spring, the block will take longer time to go back and forth because being so massive, it has a lot of inertia. So you see, the greater the mass m, the longer the period t. On the other hand, what about the spring constant? Well, if I have the same mass, but this time the spring is much stronger, much stiffer. Okay, I pull the spring to a certain amount, let go. The spring with a very large spring constant will try to pull the mass back immediately, which means the motion can repeat itself much quicker. Therefore, the greater the k value, the shorter the period t. So you see, indeed, t or omega are determined by the system itself, the spring constant and the mass attached. These are called dynamic variables. Okay, we can now go back to one of the original topics, and that is what is so simple? And what's the meaning of harmonic? Well, here's our solution. X equals a cosine omega t plus delta. Why do we call it simple harmonic oscillation? The first explanation is the term harmonic. Harmonic in our context means frequency. Simple, actually, in my understanding, has two meanings. One is simple harmonic means a single frequency. Okay, it's not made of two different frequencies mixed together. There is only one frequency, omega, or period t in it. So simple harmonic means having a single frequency. That's one meaning for it. And the other meaning, simple, means, well, it is the simplest oscillation there is. That's why we call it simple harmonic oscillation. Now, you might think that sine or cosine function may not be the simplest function in the world. How about you say, oh, how about if an oscillation goes like this? Huh? Like a square type of thing. Now, which one is simpler? Harmonic, sine cosine function, or just a whole bunch of lines, straight lines? This might be a little easy to draw, but I tell you, in reality, this type of oscillation is very difficult to achieve compared with that. It is because with any complicated oscillation, I can always use the sine cosine function to mimic it. If it's a single sine cosine function doesn't do the job, I can come up with 2, 3, 4, or whatever. I can have, 100 functions, each with different frequency. I mix them appropriately. I can get everything I want, including these very, very sharp edges. On the other hand, you don't use a single sine cosine function. You don't get these. And the thing is, this type of motion is very, very unrealistic in the world. Because look at how, see, this is x, right? And this is t. From here to there, x stays at 0. Then it abruptly goes up to a certain value, which means the speed is basically instantaneously infinite. And then it comes to 0 speed again, and jumps down with infinite speed, and so forth. So this type of motion may be easy to draw, but it's difficult to realize. Simple harmonic truly means simple, because this is the simplest type of oscillation, not only with a single frequency, but as a sine cosine function, which can be the basis of all other oscillations. Now, just because it's simple doesn't mean it's useless. Because as we learned in the second slide, you can come up with very complicated elasticity curve of restoring force versus x, as long as you don't give it a very large amplitude oscillation. That is, you just focus on this very, very small displacement. You can almost always replace with a straight line, and you have this negative kx as restoring force, and of course, you do the algebra, you find a simple harmonic oscillation. So you see, the simple harmonic oscillation is not only simple, but also it is valid in a very large number of circumstances. Because as long as the oscillation has a small enough amplitude, I can always treat it as a straight line, and therefore I get all the simple harmonic results.